So in this last video here, we're going to talk about magnetically coupled circuits. And typically what we have here is we have two inductors where we have one that has an inductance L1 and then one that's an inductance L2. And we have a dot because there's something called the dot convention. Now we're going to be able to simplify this. We're going to talk a tiny bit about the deep theory behind this, but we're going to simplify it really quickly to kind of be able to get to some good approximations of these, because when you dive into some of these equations it can kind of be a little messy here. But the idea here is that if I look at this and I, for instance, put on here an AC voltage, so maybe this is 115 volt RMS, and I'm putting that through, and it might be at 60 hertz, for instance. So I have an alternating current going through here. Now, we can go through and look at all the calculus equations and see what's going on, but the simplest thing to think here is that when you have an alternating current, through an inductor, you create a magnetic field. Which actually, and so this is just talking about the first inductor here, which can be a good or bad thing. So we're going to generate a magnetic field. Now, when you have this magnetic field being generated, what it ends up happening is this magnetic field induces a current in L2 if they are close enough. I mean, if they're close enough distance apart, even if they're not touching at all, you know, they don't have to be touching, but if they're close enough, you will actually generate a current in L2. And so I could attach some kind of load here, and I would get a current I2 going on here. Now, this is where it gets a little weird here. So I've got a current now flowing through L1 because of this power supply, so I'm inducing a current here, but now I also have a current flowing on this side, and so I'm actually going to induce a current back on this side here, because now I have current going through this L2, which is going to L2 is going to now generate a magnetic field, and that magnetic field is going to induce a current back on L1. And maybe it will interfere with I1, or maybe it will benefit it. You can probably guess which one it's going to be, because if it was going to benefit, suddenly I'd be able to, like, you know, kind of get a, you know, generator that just eventually just kind of perpetual motion kind of thing. So, you know, it doesn't make sense that, you know, this current's going to be able to, quote, help this current out, meaning making this side larger and larger. So they are going to kind of be going in opposite directions here. Now, because of these things are connected, we have something here that we label as M, and we call this the mutual inductance. And there's a formula for M, and it's K times the square root of K1, K2. And here, not K1, K2, L1, L2. And here, this K is called the coefficient of coupling. And it's between 0 and 1. if you have it equal to 0 here, as a side note, you actually mean you're not coupled at all. Now, what's important to recognize here is, if you just have two inductors, they might start interfering. Or even if you have just an inductor in a circuit, you might start causing interference because you are going to generate a magnetic field. Now, it might be small magnetic field, so it might not be a big deal, but you are going to generate a magnetic field. So some inductors, when you buy them, some fixed value inductors, are shielded. And of course, the shielding is to basically prevent magnetic field from affecting other circuits. Okay, so let's go a little bit more into what's going on here. So let's draw a circuit here. Come on, why is my eraser not working here? My laptop is starting to get a little slow on me here. So let's do another 115 volt RMS. And maybe there's some resistance here for the source. And then what I'm going to do here is actually draw what would be considered a real pair of coupled inductors here. Okay, so what we have here is that an inductor actually is going to have some kind of resistance for it because it's a wire. It's wire wound and everything. So this is kind of a model for that inductor here. So we've got some resistance for inductor 1 and then the actual inductance, resistance for inductor 2 and then its actual inductance. And then I've got my source resistance, my load, and then I'll still have my dot convention here. Now if I just draw a current in here, we clearly have here plus minus, I'll just call this V1. And then I also clearly have here a plus minus V2. I have a current here, I2 going. Now this dot convention does have meaning here, and we'll talk about that in a little bit later on. But I'm just going to show here what we end up getting here, because we talked about this inducing here. We also get this voltage here plus, and I'm going to minus, and I'm going to call this VM2. Because this is a voltage that's induced on this inductor due to this current flowing through this inductor. Conversely, we also have, or similarly, we also have a plus minus VM1, because that is the current, because we have an AC current going through this inductor here, which is generating a magnetic field which induces a current here. So we have these voltages that get induced here. And then if I look at this as my output voltage, well, this particular kind of circuit here is something very important that some of you might already know the name of. This is something that's called a transformer. And what's the idea here is that the transformer, my V out, can be transformed from 115 based on the values of L1 and L2. So based on the inductance of L1 and L2, we can actually change this voltage. So you could, for instance, have V out equaling, for instance, maybe we get 11.5 volts for V out. So this would be what's referred to as a step-down transformer. because it's stepping the voltage down. You might also be able to get, for instance, V out. Maybe we can get V out to be 220 volts. This would be a step up transformer. But one thing we want to keep in mind here is current as well. Power must remain constant. And ignoring losses due to, air or whatever the material is that is being used to make the inductor, often there's an iron core inside transformer, which is why they can be pretty heavy. But power must remain constant here. So if that's the case, if we have 115 times, I'll just say my IP, this is for my IP would be primary winding. That's what we call the left side. So this would be my power. But then on the secondary side, my power still has to be 115 IP on the secondary side, but that's going to have to be equal to 11.5 times the current on the secondary side. This would be for a step down. But what does this mean? Current goes up. So if you're stepping the voltage down, the current is actually increasing, because the power has to remain constant. Now, we're just, again, ignoring any kind of losses at this point, because for back of the envelope computations, it's fine to ignore those losses. But if we do a step up, come on. There we go. If I do a step up, well, again, this has to remain constant. The current goes down. So you never want to think of a transformer as transforming, getting more power out. In fact, you never get more power out of a transformer. You use a transformer, you're going to get power loss, because transformers heat up because there's finite resistances in those things, and so there is going to be absolutely power loss. So these equations aren't even true. If you feel your power supplies for like your computer or cell phone, how they heat up sometimes, that's because of the transformers inside them. They're heating up. It's possible it could be something else, but usually it's the transformer that's heating up, that's causing that heat on those power supplies. And so your power is not actually, changing, but my current can go up or my current goes down depending on whether I'm stepping the voltage up or stepping the voltage down. Now, to analyze a circuit like this, we can go and use my phasor analysis and everything else like that. Or what we can do here is we can make basically what is, see if this will respond here. This is being a little slow. Let me pause. You can make, not wanting to switch, that's fine, an ideal transformer. And now the analysis for ideal transformers, which is what we're going to study, is really easy. These are easy to deal with. An ideal transformer, we make some assumptions that, of course, aren't correct. We assume that the inductances are infinite, and that my coefficient of coupling is 1. And how we typically draw a transformer that is ideal, we'll still have this dot convention, which we'll talk about, but then we have something that we call the turn ratio. N1 to N2. And that N1 to N2 basically tells me how much I'm stepping up the voltage or how much I'm stepping down the voltage. So that's what we're going to start looking at next time. Now, these transformer businesses here, this concept here is actually something that's used a lot right now. If you've ever seen any kind of wireless power supply, where you can generate charge your cell phone with a wireless charger, that's because basically your cell phone has an inductor inside it, and then the charging pad also has an inductor inside it, and you're taking advantage of that. And now it's not a DC current, it has to be an AC current, so they're running an AC current through that inductor, transmitting it into your cell phone, and then that cell phone is turning that back into a DC voltage to charge the battery. And it turns out that's even how some pacemakers work nowadays. I don't have a pacemaker, but I've got a battery implanted that is for an electrical stimulator for my face, and that is a wireless charger. And when I charge it at night, looks like a giant washer that I put on my chest. It's literally just a big coil of wire. I put a big inductor on my chest, and there's an inductor inside my battery unit in my chest, and it charges wirelessly through me. So it's a really cool technology. So we are going to talk about transformers, though, in more detail on how we actually can use ideal transformers.